Okay, so this week we will learn about the other type of optimization problem. This one we call production and procurement planning. But you will learn that you will see that production procurement planning it's somewhat similar to what we have learned about the multi-period optimization problem. This case, a food is manufactured by refining raw oils and blending them together. Imagine that we run a plant, and our product gets its oil, okay, edible oil, of course, and it can produce by we can purchase the raw oils, okay, of five types. We have vegetable oil one, vegetable oil two, non-vegetable oil. Yeah, we use oil one here. It's represent uh, non-vegetable oil. Non-vegetable oil one, non-vegetable oil two, non-vegetable oil three. Okay, we have five types of oil, and each oil may be purchased from immediate delivery in January, or we can bought on the future market for delivery in subsequent months. Assume that the price for each type of oil and in each month given in this table. Okay, so for this table, the first column is a type of oil. We have vegetable oil one, vegetable oil two, non-vegetable oil one, non-vegetable oil two, and non-vegetable oil three. Okay, and each column, the second column, it's the first month. We can call it January, February, March, April, May, and June. Okay. And in each element is the cost, okay, the price of oil we purchase. It's in the unit of dollar per ton. And the final product, once we purchase oil and we process it, of course we we process it by mixing different type of oil and then go through the processing. Okay. And once we get the final product, is a produced oil, we can sell it at $150 per ton. Okay. And there are, several conditions. The first condition is vegetable oils and non-vegetable oil require different production line for refining. So then that means, uh, for vegetable oil, no matter we buy vegetable oil one or vegetable oil two, it will be processed in the same process, okay, using the same process. So it is not possible to refine more than 200 tons of vegetable oils per month, okay. And for non-vegetable oil, the maximum capacity is 250 tons per month. That means, each month we can we can purchase vegetable oil one, vegetable oil two, non-vegetable oil one, non-vegetable oil two, non-vegetable oil three. Okay. And of course, we have to mix all this oil, right? However, before mixing it, for vegetable oil, we can mix it and process, yeah, using the same process, okay? And the maximum processing for vegetable oil is 200 ton. And for non-vegetable oil, the maximum capacity is 250, okay? And we assume that there's no loss of weight in the refining process, okay? And the cost of refining may be ignored, okay? So that means, we don't have to consider these loss of weight and also the cost for refining process. And it is possible to store up to 1,000 tons of each raw oil for use later. Okay, so we have five types of oil. We have storage tank for each type of oil. for vegetable oil 1, vegetable oil 2, non-vegetable oil 1, non-vegetable oil 2, and non-vegetable oil 3. And there is a cost of storage. The cost of storage for vegetable and non-vegetable oil is $5 per ton per month. Okay, so you can purchase it. If you don't use it, I mean refinement and process it, then you have to store it, right? And the cost for store of this oil is $5 per ton per month. Okay, and the final product cannot be stored. That means, well, you cannot process it first and then keep the processes finished product to sell in the future. And there's no there is a technological restriction on hardness of the final product. So the final product, the hardness must be between 3 and 6. Okay, so and each type of oil has certain value of hardness. For example, vegetable oil 1 is 8.8. Okay, vegetable oil 2 it's 6.1. For non-vegetable oil 1 is 2, non-vegetable oil 2 is 4.2, non-vegetable oil 3 is 5. Okay, so the final product, well, it's a mix between 5 types of oil, right? So each type of oil contribute to the hardness. Okay, so we can estimate it using linear. Okay, it's a, well, interpolation between on this raw oils. Okay, so the question is on a policy. What buying and manufacturing policy should the company pursue in order to maximize profit? And there's also, well, another condition. At present, there are 500 tons of each type of raw oil in storage. Okay, and it is required that these stocks will also exist at the end of June. Okay, so we consider 6 months, right? January to June. Okay, and each month, what are we going to do? We purchase oil. Okay, and we have to, well, consume some amount of oil and mix it, process it, and sell to the market. Okay, and the price for each type of oil in each month is a difference, and but the final product, the price of the final product, it's constant, all right, at 150. Okay, so what are we going to do? Our objective is to maximize the profits. Okay, so we have to consider the model of the profit first. Okay, so we have to write down the profit. We're going to maximize the profit. Maximize the profit. So what about our profit? Profit is revenue, right? Subtract by the cost. So this is revenue subtract by cost. And there are 2 types of cost. The first cost is the the cost for purchasing the oil. I mean raw oil, okay? Purchase of oil. And the next one is storage, right? Okay. So for revenue it's, well, very simple. So it depends on, because the price is constant, so it depends on the amount of oil we sell each month. Okay. Though the amount of oil, it's of course it's a mix, right, between the amount of each type of oil that you selected to process, right? Because the our final product is a mix between some part of a vegetable oil one, vegetable oil two, non-vegetable oil one, non-vegetable oil two, and non-vegetable oil three. Okay, we select some part and then we refine it and mix it and to make a final product. Okay, so it's 150 times by the amount of final product. Okay, okay. So what about the cost? For cost, it depends on the amount of oil we purchase at each month and each type of oil, right? So the cost is not constant. It depends on the cost of each type of oil, each month, right? And time with the purchase, the amount of oil we purchase at each month, each type of oil also. And what about the storage? The storage cost is, it's quite simple. It's a 5 times with the amount of oil we store. Okay, we can use T, okay? T standing for, yeah, T. But it's not TIJ. I mean, it should be summation of T, right? Because, yeah, this one also, yeah, we have to summarize it. And this one, amount of final product, it's, if write, we can write this way, summation of what we sell, IJ, okay? Summation of the amount of oil we sell. Okay, so now we look at our decision variable. So decision variable, you see that what we need, the amount of each type of oil and at each month, okay, we're going to, sell, right? Also, we need a variable to represent the amount of oil, each type of oil, each month, we're going to purchase. And this is the important uh, variables for multi-period optimization problem. TAJ represent the amount of oil, each type of oil we store at the beginning of each month. Okay, so the structure of the decision variable look like this. Okay, we can okay use a matrix. Okay, this way. This is month, right? This is month. And this is oil, each type of oil. We have 5. Okay, so we have 6 here. We have 5 here, right? So for P, we use PIJ. I is standing for type of oil, right? This is type of oil, and J is month. Okay, and we need storage TIJ again and SIJ. Okay, so I is running from 1 to 5, okay? And J is running from 1 to 6, okay? We have 6 months. Okay, so this is the objective function. We're going to maximize this, okay? And this profit can be written as, okay, revenue first 150 times with, well, summation of what we sell, okay? And for the cost, we have two type of cost. The purchase cost is the amount of each type of oil at each month we're going to purchase time with the cost, the price. Okay, I'm going to show you again the price. Well, it's look like this. Okay, you see the cost for each month. Okay. Okay, and the next model for the cost is storage. For the storage, it's very simple. It's 5, okay, which is the cost to store each type of oil, okay, for each month. So we time it with the amount of oil in the tank, okay. So what about the constraint? The constraint we have, well, first the constraint we have, okay, we know that at the beginning the oil we at the beginning, so T I1, right? Where I is running from 1 to 5 in the storage. At the beginning, we have 500, right? Yes, 500. Okay. So, well, we have 5 constraints for this. Okay. And what else? At each month, each type of oil must be, of course, greater than 0. It's non-negative, right? And it must be less than 1,000 because this is the maximum of the amount of oil we can store. Okay. Each type of oil and also each month. And what about the other? We have more of this. Okay. At each month, we cannot refine more than 200 ton of vegetable oil. So for, sorry, well, the amount of oil one at each J month plus oil two at each J month must be less than 200. Okay. We have 6 months, right? So we have 6 constraints of this. And what else? S 3J plus S4J plus S5J must be less than 250. Okay. Okay. We also have 6 constraints of this. Okay, right? Now, welcome to the constraint regarding the, well, the conservation of oil, each type of oil. Okay. So at each month, let's say if at the beginning of the January, we have TI1, right, in the tank. Plus, we're going to purchase it the first month, okay? And what we sell in the first month, okay? Subtract by what remain in the tank, okay? in the second month must be 0. Okay, it's a conservation of mass, right? For for yeah, each type of oil. Okay, so this is only the first month. Okay, so we need 5 constraints. Okay, for yeah, look like this. Mm-hmm. And we for the second month TI2, right? What remain in the tank at the beginning of the second month plus what we purchase in the second month subtract by what we sell in the second month. Well, and what remain in the tank at the beginning of the third month must be 0. Okay. We also have 5 constraints of this. And the next one is TI3 plus PI3 I3, okay, TI4 must be 0, okay, and for 4 plus PI4, yes, SI4 plus TI5 must be 0, okay, and for the fifth month, okay. What about the last one? The last one is the last set is the at the beginning of the 6th month in June, TI6, okay, what remain in the tank plus what we purchase subtract what we sell, okay. However, we don't have TI7, right? So we have to subtract by 500 and it becomes 0, right? Because why we do this? Because it's a constraint, right? Right? We have to maintain the stock, okay? We have to fill up the stock. So each time at the, well, after 6 months, each type of oil must be, well, in the stock must be 500 ton. Okay, so we're going to translate all these things into Excel. Okay. Remember that we need non-negativity, right? We have negativity constraint here. What else do we need? We need a Sij must be positive, and also Pij must be positive, right? Okay, so in Excel, well, I create a file like this. I put the, well, each element here from B3 to G7. Here we have a 5 by 6, right? Matrix. This Okay, these cells represent each element of Pij. Okay, we have 5 row and 6 column. Okay, and we have S. Okay, here 5 by 6 again. We have 5 rows and 6 column to represent each element of S. Okay, and for T, we have again 5 rows and 6 column to represent each element in the Tij. Okay, so what about I put the cost here. This is the price for each type of oil and at each month. Okay, it is 5 by 6 again. And while I put the formula here in this column as in this cell as a cost. No, it's not cost, it's revenue. Revenue is, well, you see that it's $150 per ton, right? And this is a summation of S, okay, with sum from I3 to N7, okay? And what about cost? We have cost here, which is the, sorry, okay, it's quite complex because we have to time Pij while with Cij and we sum everything. Okay, so you see that B10, right? No, B10 here with B3 plus B11, this with time with B4. Okay, each element I time the price with the amount of purchase oil. Okay, and sum up each element. Okay. Oh, and the next one is a cost too. Cost, this cost is, well, 5 times with sum of Tij. What about Tij? Tij is here. Okay, it is the amount of oil in the storage tank at each month. Okay. Okay, so the objective function is revenue subtract by cost 1 and cost 2. Okay. And we have a constraint here. It's the this one. This TI no TI1, right? TI1. I mean T11, T21, T31, T41, T5, T51 must be must be 500. Okay. Hmm. Yes, maybe it's 500. This might be 500. Okay. And this is the, what is it? What we purchase plus what we, well, in the storage, okay, plus what we purchase, subtract by what we sell, subtract by what remain in the tank in the next month must be 0, okay. This also, yes, must be 0. This also must be 0. Okay, you have to repeat all these things for, okay, each type of oil. And from 5/1 to, from first month to fifth month, right? But for the, what's it? The last month is quite, it's different. Okay. Okay. Okay, we go, well, further down. Okay, so this is the fifth month. No, no, not fifth, sixth month. Okay, last month. You see that we have to subtract by 500, right? So you can write this way, or well, we can move this 500 to the other side, like, yeah, this way. It's possible also. Okay, okay. And this one is constraint for, well, refinement of the constraint on the capacity of the refining process of vegetable oil must be less than 200 ton, right? Okay, now we reach the the constraint on the capacity of the refinement process of the non-vegetable oil. Okay. Okay. So, oh, I haven't shown you the constraint on the hardness yet. Okay, let us go back to the derive of the hardness, because here it's the hardness, I think. Yes, it should be hardness, right? Okay, we stop Excel here and go back to derive of it. Okay, so we're going to share these. Okay. Okay, for the hardness, we know that the hardness, how to calculate the hardness of the final product. Let's say, well, we start from the final product for first month. Okay, so we mix between S, first month should be one, right? So S11, sorry, yeah, let's write J. Okay, J represent the month, right? SI S1J is the amount of oil, vegetable oil one, that we use to blend and produce the final product, right? So the hardness of this one is 8.8, okay? So 8.8 times with the amount of vegetable oil one, okay? Plus 6.1 is 2J, plus 2 is 3J, okay? Plus 4.2 is 4J, plus 5 is 5J, okay? And we have to divide it with the amount of, okay, oil that we use in the first month to produce the final product. Okay, and this value should be between 3 and 6. Okay, And you see that if we write the constraint this way, it's not linear. Why is not linear? Because you have the this variable divided by variable, which is nonlinear for sure. Okay, but we know that this value must be positive and it cannot be zero, right? So we're going to multiply this expression with this value. Okay, so we obtain 3 times width is, sorry, 1j plus 2j plus is 3j plus is 4j plus is 5j. Okay, and this value should be, well, less than or equal 8 by 8 is 1j plus 2j plus 2, well, is 3j plus 4.2 is 4j plus 5, 0 is 5j, okay? And it must be lesser than 6 times by is 1j plus is 2j plus is 3j plus is 4j plus is 5j, okay? Okay, so we take this part first as inequality constraint, right? And we take this part as another inequality constraint, okay? So we can write two constraints, inequality constraint for each month, okay? So we get 10 constraints out of this, 10 inequality constraint out of this. Okay, this is the first one. Okay, this is the second one. You see that? Wow, I write. This is 3, right? And for this one, it's 6, okay? Well, 3. This one should be 6. This one was 3, and this one should be 6. 3 and 6. So 3, this one is 6, and 3 and 6, okay? Okay, and the next constraint is, well, the amount of oil in the storage tank must be less than 1,000, okay? Mm. Okay, so, well, we finished the model, and now it's time to optimize it. Okay, the objective function is this cell, okay? And we're going to maximize it by changing this cell, the cell that I highlight in yellow, okay? Can write this way. Well, it's a box of from B3, right, to G7, and then we move to I3 to N7, okay? And P3 to U7. Okay, good. Oop. Oh, sorry. Oh, what happened? Okay. Okay, and then input each constraint to the system. Okay, and then make unconstrained variables non-negative, and we use simplex LP. Okay, nope, and then solve. Sorry, it's not A25. Sorry, change already. Okay, B20. B20 is our objective. Okay. Okay. So we got the result. Okay. It's quite complex in especially in the case that well we have larger model. It's maybe well it's prone to error. Okay. And later I will show you how to well if you don't want to use Excel, of course we can model it using MATLAB or other software, but I'm going to show you how to do it in MATLAB, okay, through YAML later, okay. Now we move to the next example first, and then later we cover the on the how to formulate the model in MATLAB, okay. It will be much shorter because we can write a code. Mhm. Okay, so now we move to the next problem. We call it refinery optimization. For refinery optimization, imagine that we are running a distillation plant that the plant can accept crude oil, okay, crude oil from different sources, of course. And for distillation column, of course, if we feed those crude oil to the distillation process, we produce different type of product like light naphtha, medium naphtha, heavy naphtha, light oil, heavy oil, and residue, the rest. Okay. And for yeah, imagine that in this problem we can accept two crude oils, okay, and then we produce from distillation process we can produce light naphtha, medium naphtha, heavy naphtha, light oil, heavy oil, and residue. And of course, we can blend light naphtha, medium naphtha, heavy naphtha to produce petrol. Okay, but of course, for light naphtha, it has a certain, no, not limited, it's certain value of octane number. Medium naphtha also have octane number. Heavy naphtha also have a certain value of octane number. And if we blend it, maybe we cannot reach the uh, stipulation quality of the product for the octane number. Okay, we can boost the octane number by by feeding the naphtha we produce here to reformer. By feed light naphtha, medium naphtha, heavy naphtha to reformer, we can produce reformed gasoline. We call it reformed gasoline. And for reformed gasoline, it has higher octane number, and we can blend this reformed gasoline with light naphtha, some amount of light naphtha, medium naphtha, and heavy naphtha we produce from the distillation column. And for light oil and heavy oil, of course, we can blend it to form the product directly, or we have another choice. Okay, alternatively, we can feed light oil, heavy oil to cracker. Okay, and from the cracker, it produce cracked gasoline and crack oil. Okay, for cracked gasoline, of course, it has quite high octane number, though the octane number is lower than reformed gasoline, but it's higher than light naphtha, heavy naphtha, or medium naphtha. Then we can blend all these things, okay, to 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 make our product like, yeah, petrol. Okay. Also, crack oil, we can send the crack oil. Well, we can blend it with light oil, heavy oil. Okay, to form some products. Okay, I'm going to explain later in detail. Okay, so we have several, well, ingredient, right? From distillation column, we have light naphtha, medium naphtha, heavy naphtha, light oil, heavy oil, and residue. Okay, and from reformer, we have reformed gasoline. Okay, from cracker, we have crack gasoline and crack oil. Okay, and we have final product of regular premium and no, regular petrol, and PP standing for premium petrol. For regular petrol, while we can blend light naphtha, medium naphtha, heavy naphtha, reformed gasoline, and cracked gasoline to form regular petrol. And for premium petrol, we use the same ingredient but different formula in order to meet the higher requirement of premium petrol. Okay. So you see that, well, we have to decide, right? The amount of naphtha that we send, how much we send to reformer, right? And how much we send directly to blend into regular petrol or premium petrol. Okay, we have more products. We have jet fuel. Jet fuel, we produce jet fuel by blending light oil, heavy oil, and crack oil and residue. Okay, and we have product of fuel oil. For fuel oil, we blend light oil, heavy oil, crack oil, and residue. Okay, and the last one is lube oil. For lube oil, we use residue and we process residue and in order to make lube oil. Okay, so we have all these products, and also, well, we have to design. Now we look into the detail of the problem. Starting from distillation. Distillation column can accept two crude oil, crude one and crude two. So we have to decide how much of crude oil, crude one and crude two, we have to purchase, okay, and fit to distillation column. And for distillation column, of course, light naphtha, medium naphtha, and heavy naphtha has different value of octane number, right? So for light naphtha, it has 90, okay, octane number of 90. And for medium naphtha, the octane number is medium, yeah, is 80, okay? And heavy naphtha, it has 70 octane numbers, okay? And if we send crude 1 to distillation column, the yields are shown in this table. Okay, for 1 barrel of crude 1, crude oil 1, okay, we get like 0.1 of light naphtha, zero point 0.2 of medium naphtha, 0.2 of heavy naphtha, 0.12 of light oil, and 0.2 of heavy oil, and 0.13 of redstone. Okay, so for 1 barrel of C2, okay, the yields are shown here in this table. All right, so we move to the next process, which is a reformer. Okay, reforming process. The naphtha can be used immediately for blending into the product, right? Or we can design how much we fit to the reformer. Okay, and reformed gasoline has higher octane number, as I mentioned earlier. Octane number of the reformed gasoline is 150. 15, okay, 115. And the yield of reformed gasoline from each barrel of the naphtha, different type of naphtha are given here. So if we fit 1 barrel of light naphtha, we yield zero point 0.6 barrel of reformed gasoline. And 1 barrel of medium naphtha yields 1 point, no, not 1, 0.52 barrels of reformed gasoline. And 1 barrel of heavy naphtha yields, well, 0.45 barrels of reformed gasoline. And the next process is cracking. Okay, the light oil and heavy oil can be fed to the cracker. Okay, cracking process. And the product of the from this process is crack oil and crack gasoline. For crack gasoline, it has octane number of 105. Okay, so the yield is 1 barrel of light oil yields 0.68 barrels of crack oil and zero point 0.28 barrels of cracked gasoline. Okay, and if we decide to feed heavy oil, 1 barrel of heavy oil will yield 0.75 barrels of crack oil and zero point 0.2 barrels of cracked gasoline. Okay, and as I mentioned earlier, crack oil, we use crack oil to blend for fuel oil and jet fuel. Okay, and for cracked gasoline, it's used for blending of petrol. And residuum, well, of course, from distillation column, we have light naphtha, right? Medium naphtha, heavy naphtha, light oil, heavy oil, and we have residuum. For residuum, we can use it for blending the jet fuel or fuel oil, and we can design, well, to we can fit residuum to produce a lube oil, and 1 barrel of residuum can, well, make zero point 0.5 barrels of lube oil. Okay. So now we move to the blending process. For blending process, of course, for petrol, we have 2 types of petrol, regular and premium petrol. And while we can produce it by blending naphtha, 3 types of naphtha, light, medium, heavy naphtha, right? And reformed gasoline, cracked gasoline, okay? The condition is the octane number for regular petrol must be greater than 84. And for the premium petrol, the octane number must be greater than 94. Okay. And the concerns about jet fuel. Now we move to the jet fuel. For jet fuel, the vapor pressure must be less than 1 kilogram per square centimeter. The vapor pressure for light, heavy crack oil and residuums are 1, 0.5, 0.6, 1.5, and 0.05 kilogram per square centimeter. Okay. And the next one is fuel oil. To produce fuel oil, while we use light oil, crack oil, and heavy oil residue, and it must be blended in the certain ratio. So the ratio is 10 to 4 to 3 to 1. Okay. We have more condition. Okay. The daily availability of crude 1 is 20,000 barrels. And the daily availability of crude 2 is 30 barrels. Okay. And for distillation, we can refine at most 45 barrels of crude. Okay. And for the capacity of reformer is 10,000 barrels a day. And capacity of the cracker is 8,000 barrels a day. And the daily production of lube oil must be between 500 to 1,000 barrels. Okay. And premium motor fuel production must be at least 40% of regular motor fuel production. Okay. So the premium must be at least 40 of regular petrol. Okay. And the profit contributions from the sale of final products are shown here. Okay. Premium petrol, the profit is 700, regular petrol is 600, jet fuel is 400, fuel oil is 350, and lube oil is 150. Okay. So the question is, how should we operate this process? Okay. In order to maximize total profit. So it's clear that our objective function is profit, right? So we're going to maximize the profit. So we have to write the profit as a function of distant variables. We have difference, well, distant variables, okay? And we have to design, okay, the distant variables first. We know clearly about the objective function now. Now move to distant variable. The distant variables, we have to design the amount of C1 and C2, right? And for Ln, Mn, Hn, Lo, Ho, and R, it's divided by C1, C2, right? Okay. So, but we have to design because like naphtha, we can send light naphtha directly to blend for regular petrol or premium petrol, or we can send light naphtha to reformer, right? So for light naphtha, it can go to produce to reformer, right? To make reform gasoline or to blend as a regular petrol or premium petrol. Okay. So these must be the our distant variables. Okay. Medium naphtha and heavy naphtha are also the same, right? We have to decide how much of the medium naphtha to send to blend for premium petrol, regular petrol, or to reform gasoline. Okay, to reformer in order to produce reform gasoline. Okay, heavy naphtha also follow the same pattern. And you see that this one light naphtha that we fed to reformer, medium naphtha we send to reformer, heavy naphtha we send to reformer. While it we reform them to produce reform gasoline. I use RG here to represent it. And RG, we follow the same route. Okay. For RG, we can send RG to blend for regular petrol or premium petrol. And then we reach the final product. Okay. Yeah. Okay. Now we follow the light oil. Light oil can be well blend to form fuel oil or jet fuel, or we send it to cracker. Okay. Heavy oil also, we can send it to blend for fuel oil or jet fuel, or we send it to cracker. So you see that LO to C here and HO to C, which is light oil, we send to cracker. We have two products, crack gasoline and CO. It represents crack oil. Okay, so for CG, crack gasoline can be well sent to blend for regular petrol or premium petrol. Okay, crack oil can be sent to blend for jet fuel and fuel oil. Okay, I use CO2JF and CO2FO. Okay, here, and for residue can be sent to form lube oil. Okay, or it can be blend for jet fuel and fuel oil. Okay, now you see the structure of the decision variables we have. Now the blending process, we have Ln to Rp, right? Mn to Rp, Hn to Rp, Rg to Rp, Cg to Rp, right? All these things blend to form Rp. Rp is the amount of regular petrol we produce. And we follow the same pattern, but this time it's PP. PP is premium petrol, okay? And now we move to jet fuel. Jet fuel receive light oil, right? Heavy oil, crack oil, and redstone. Okay. And fuel oil, well, we follow the same pattern. And the last one, redstone. Redstone can be processed to produce lube oil. Okay. We have uh how many products we have? Five, right? Regular petrol, premium petrol, jet fuel, fuel oil, and lube oil. Okay, five products. Okay, so the objective function here, we can write our profit at 700, which is a contribution, profit contribution of premium petrol, right? Plus 600 RP, regular petrol, and 400 JF, jet fuel, and 350 of fuel oil, plus 150 of lube oil, okay? And constraint, for constraint, you see that for light naphtha, it is a function of light naphtha equals zero point 0.1 C1, right? Plus 0.15 C2. You see this from this value, I mean this coefficient is a yield of light naphtha if we use if we fit 1 barrel of C1 or 1 barrel of C2, right? Okay. Now we move to medium naphtha, heavy naphtha, right? And also light oil, heavy oil, and redstone, okay? And the condition, one condition is the crude oil, the first crude C1 must be less than 20,000, C2 must be less than 30,000, and this while C1 plus C2 must be less than 45,000, which is the maximum capacity for our distillation column. Okay, and this is light naphtha. Okay, from light naphtha we produce light naphtha must be well equal to light naphtha that we send to regular petrol. No, reform. Okay, reformer we send to regular petrol and premium petrol, and MN also the same, HN also the same. And for reform gasoline, it's well because we send LN to a light naphtha to produce to reformer, right? And 1 barrel of light naphtha produce zero point 0.6, okay, of reform gasoline. And for medium naphtha, it produce 0.52 barrel, okay, of reform gasoline. And if we send 1 barrel of heavy naphtha, we got 0.45 heavy naphtha, okay. And the amount of the light naphtha, medium naphtha, heavy naphtha we send to reformer must be less than 10,000. Okay. And reformed gasoline we produce must be equal to uh, reformed gasoline we send to produce the regular petrol and premium petrol. Okay. Okay. We follow the same concept, but this is around the cracker. Okay. We follow light oil, heavy oil. Okay. And the amount of light oil and heavy oil we send to cracker must be less than 8,000, okay? And now we move to this one. It's lube oil. Lube oil, 1 barrel of redstone produce only zero point 0.5 of lube oil, okay? And this is the condition for octane number, okay? For regular petrol, it's 84, right? You should write this way because this is a linear function. If you divide it, divide this expression with RP, it becomes nonlinear, right? So you have to multiply both sides of inequality with RP, right? Okay, this is 94. Okay, the same for the Weber pressure. Okay, we convert it to linear function. Okay, okay. And we have to specify non-negative, right? Our variables will be greater than 0. Okay. So for today, well, please write all these things in Excel, okay, by yourself, and then well, we we will discuss at 1 o'clock. If you have any questions, well, at that time, just ask me, okay? Okay, I'm going to upload this video for you first. Okay. Okay, see you.